Now we're going to explain how to use the snake lemma to do an interesting calculation of homology groups. So we're going to be looking at the boundary of a simplex. So we've defined homology for abstract simplicial complexes, so we need to work with the abstract simplex. So remember that way that works. So we have to have a vertex set, so that's going to be the set of numbers from 0 up to n. And we have to declare some subsets to be simplices, and the way it works for the abstract simplex, we just declare that every possible subset sigma of v is a simplex, provided it's not empty. Empty subset never counts as a simplex. So what's the homology of this complex here? Okay, so well, it's got a cone point. Right? We mentioned this before. We can just choose any vertex, and that's always going to be a cone point. And for any complex that has a cone point, the homology is very simple. You just get the z as h0, and the other homology groups are trivial. Okay. But things get more interesting if we look at the boundary. Okay, so by the boundary of the abstract M simplex, we mean the subcomplex. So we've got the same vertices, 0 up to n, and mostly the same simplices. But the full set itself, 0 up to n, that doesn't count as a simplex. So that means in terms of geometric realization that we just kind of don't fill in the middle. We've just got the boundary. So our task is going to be to calculate the homology of the boundary of the n simplex. So to do that, we're going to use the snake lemma in terms of these complexes here. Well, the main one that we're interested in is the chain complex for the boundary of the abstract simplex. We're going to call that U. And that sits inside, that's a subcomplex of the chain complex for the full simplex, which we're going to call V. And then we define W to be the quotient, V star mod U star. So that means that we've got a short exact sequence. So U star includes in V star, and then the quotient is W star. So U star, V star, W star, that's a short exact sequence. And so by the snake lemma, that gives us a long exact sequence like this. We've got kind of the middle bit here, the homology of U, homology of V, homology of W, and then you've got this delta that goes from HK plus 1W to HKU. So remember this, so homology of V is the homology of this full n simplex, and as we said, that's mostly 0. It's mostly 0. So so most of the time, both this HKV and the HK plus 1V are both 0, and that means that the HK plus 1W and HKU are the same. Yeah, but then this W is also mostly 0, okay, because there's very little difference between V star and W star. So W star is mostly 0, so most of the time, actually, this 8K plus 1W is also 0, and the HKV is 0, and then that forces by exactness HKU to be 0. Let's recall how that goes, right? I mean, if this if HKV is 0, then the kernel of this I lower star is the whole of HKU. But if HK plus 1 W is 0, then that means the image of delta is equal to U, so is equal to 0. So the image of delta is 0, then that's the same as the kernel of I lower star, but then the kernel of I lower star will be the whole thing, so that forces HKU itself to be 0. So that's what happens kind of most of the time. We just need to work out and be a bit more careful, specify exactly what the exceptions are to that situation. The first thing to note, right, is that if we look at this boundary of the n simplex, that's basically the same as the n simplex, except that the kind of the top thing, top full n simplex is just missing. So that means that your Wn is 0. So Wk is 0 mostly, except that there's this missing n simplex, which gives us an extra generator for Vn that's not present in Un, so we just get a copy of Z as Wn. Okay. So Wn is Z, and all the other Wk's are 0. So that, and of course that forces the boundary of the complex W to be 0, right? You've got differential has got to be 0. I mean, you've got a d going from wn to wn minus 1, but wn minus 1 is 0, so that's forced to be 0. You've also got a d going from wn plus 1 down to wn, but the wn plus 1 is 0, so that d is also forced to be 0, and all the other d's are just going from the 0 group to the 0 group. And so because the differential is 0 in the complex w, that means that the homology is just the same as the original thing. Okay, I mean the kernel of d is the whole thing, and the image of d is 0, so kernel of d modulo image of d is just the same as the original w. So we're seeing that hnw is z, and all the other hkw's are 0. Okay, so that tells us about the group's homology of w in this long exact sequence. Okay, so then for the rest of the proof, we're going to assume that n's bigger than 1. I mean, there's just some tiny little extra points to deal with in the case n equals 0, n equals 1, and we're going to leave those to the reader. So now if k is different, k is not 0, and k is not n minus 1, then so k is not 0. I mean, the only homology group of v is that h0v, so k is not 0, that means that our hkv is 0. And k is not equal to n minus 1, so k plus 1 is not equal to n, so the hk plus 1, the only homology group of w was the hn, so the hk plus 1 w is 0. So we're seeing we've got an exact sequence 0 to hku to 0, and so hku is 0. Okay, so that happens except in every case except for the case k equals 0 or k equals n minus 1. Okay, so what about these exceptional cases? Let's look at H0U. So we've got a exact sequence like this, H1W, and then the connecting map to H0U, H0V, H0W. So remember, the only homology group of W is HNW, so that H0W is just 0. And then H0V, as we said here, H0V is just a Z. Then we've got our H0U, which is what we're trying to find. And then we've got our H1W. Remember, the only homology group of W is Hn, and n is not equal to 1 by this assumption, so H1W is 0. Okay, so we've got an exact sequence of 0 to H0U to Z to 0. And this was one of these basic facts about exact sequences. So this map here is 0, so that forces this map to be injective. This group here is 0, so this map is 0. That forces this map here to be surjective. So this map in the middle is both injective and surjective. It's an isomorphism. So that means that H0U is just Z. We proved that for any abstract simplicial complex K, H0K is the free abelian group generated by the path components, and because n's at least 2, it's easy to see that the boundary of the simplex is connected. As pi 0 as only a single thing, H0K is just Z. That's another way to see this result here. Then we wanted to know about this other possible exception, k equals n minus 1 case. So we're looking here at hn minus 1 of u. That fits in the exact sequence, hnv, hnw, and then the connecting map delta that shifts that dimension down and get hn minus 1u, hn minus 1v. So again, v only has a homology in degree 0, so this hn minus 1v is going to be the 0 group. And then this hnv here also is going to be the 0 group. And then we've got this HNW, which we said was Z, and then we've got this delta. So again, we've got this sort of situation, a group 0, then a map, and then 0, and the thing's exact, so the map in the middle is forced to be an isomorphism. Okay, so this delta from HNW, Hn minus 1u is an isomorphism, and so in particular this Hn minus 1u is a copy of Z. So we've shown that the this homology of this abstract simplicial complex, you've got a Z in degree k for k equals 0, a Z for k equals n minus 1, and all the other groups are just 0. So that's what we did for a case where n is at least 2, and let's just mention what happens n is 1. I mean, n is 1, then delta 1 is just like an interval, the boundary of delta 1 is just 2 points, and so h0 of it is z squared, and everything else is 0. So it's basically the same as this situation here. So here you've got a z in degrees 0, z in degree n minus 1. In the case n equals 1, you've got the two z's, so they both appear at degree 0. So that's what we get for this particular abstract simplicial complex, the boundary of delta n. And it's a fact we've discussed, we haven't proved yet. It's going to be right at the end of the course when we actually start get to the proof of this. But it's a fact that the homology of space X can be defined as a kind of homotopy invariant way, as a functor of spaces and homotopy classes and maps, in such a way that that if we take a geometric realization of K, that's a space, and we take the homology of that, well, that's just the same thing as the homology of the simplicial complex as we've already defined it. So if you assume that, then it's meaningful to talk about the homology of the n-sphere, and that's going to be the same as the homology of K for any complex K, such that the geometric realization of K is homeomorphic to the n-sphere. So okay, so we should take K to be if we take our K to be the boundary of the n plus 1 simplex, then that's homeomorphic to the n-sphere. And so we get the homology of the n-sphere. You get a K in degree 0 and n. It's a typo, should be n instead of n minus 1. And then the homology of K the homology of Sn in degrees K different from 0 and n is just 0.